We are in AP Review FRQ Topic 2, which is Graphical Analysis. This is a topic that is almost always found on the AP FRQ Calculus part of the test. It deals with fundamental theorem of calculus, as well as all of our analysis of graphs with concavity, points of inflection, maximums and minimums, increasing, decreasing, all of those concepts. So this is super important for calculus, and that's why it's found so often on the AP exams. Let's do a brief review of the fundamental theorem of calculus. Fundamental theorem of calculus, abbreviated FTOC. We began fundamental theorem of calculus before we even called it the fundamental theorem of calculus when we first started our integrals as area under a curve. This integral represents the area under y is equal to x cubed from x equals 1 to x equals 3, and when we evaluate this definite integral, we take the antiderivative of x cubed. That would be 1/4 x to the 4th, or x to the 4th over 4, and we evaluate it from x is equal to 1 to x is equal to 3. That's the fundamental theorem part of it, and so we get 1/4 of 3 to the 4th minus 1/4 of 1 to the 4th. And this is our f of b in the fundamental theorem. This is our f of a in the fundamental theorem. If f prime is equal to our original function x cubed, so which it is because this is f here. That's f, and if you take the derivative of f, you do get x cubed. So we get the fundamental theorem says this: the integral from a to b of the derivative of f is equal to f of b minus f of a. And we used it even before we learned what the fundamental theorem of calculus actually says. But that is true. And we can take this and reverse it, of course. F of b minus f of a must equal the integral from a to b of f prime. And if you think of it this way, if you have a rate or a derivative, and if you're given any value of the function, you can get any other value that you like. So if you know the rate and a value, you can get any other value. And that's most often how we see it in these types of problems. There's another form of the fundamental theorem of calculus, and that looks like this. If you take the derivative of an integral, if you take a derivative of an integral, and if I'm taking the derivative with respect to x, I'm going to need to see some x's up here on our boundaries, so I'm going to just make this up. I'm going to say let's go from 3 to x of some function. Now I could call this f of x here, but I don't want to confuse these x's with this x, so I'm going to call this f of t. Nothing magical about the t, it's just another variable, just so that I can have an x up here. If I take the derivative of this integral, then this is going to equal the function at the top boundary. Always start at the top boundary. The function at that top boundary times the derivative of that top boundary. And the derivative of x with respect to x is 1. And then we go to the lower boundary. Put that in for t. So minus f of 3, because we replace the t with the 3, and now you're going to multiply by the derivative of 3 with respect to x. Well, the derivative of 3 with respect to x is 0, so that term goes to 0. So we're left with just f of x. So if you take the derivative of an integral with the top boundary x and the bottom boundary any constant, then you just get back your function. Okay? Derivative of an integral. They kind of, remember, integral is an antiderivative, so derivative of antiderivative. It kind of makes sense that they would kind of cancel each other out. Let's look at another example. Let's say that we have, instead of 3 to x, let's say that we have 2x to x squared of some function. So we begin with the top boundary, put the top boundary in place of the t in your function, and then we're going to multiply by the derivative of the top boundary, 2x, minus, now we're going to put the lower boundary in place of t, f of 2x, times the derivative of that lower boundary is 2. Okay, let's say that we have sine x to 3x squared, and we're taking the derivative of that integral. And I'm going to actually make up a function here. Let's say we have natural log of, let's say t squared, dt. So I'm going to start at my upper boundary, replace t with 3x squared. So we'll have ln of 3x squared, right? And then we're going to multiply by the derivative of 3x squared. Now, no ambiguity. Let's put that natural log in brackets so that it does not look like the 6x is part of this argument. Minus natural log of, replace the t with the sine x. So we'll have sine x all squared, which is sine squared x, times the derivative of sine, which is cosine. And again, no ambiguity, put that natural log in brackets. So that's just a really brief review of the two forms of the fundamental theorem of calculus. Now let's take a look at your some FRQs. So grab your Topic 2 worksheet, and we are going to start by doing number 1 together. Okay. All right. Number 1 is from 2018. It was number 3. All of these are going to be no calculator, so there's no way to even use a calculator on them. Even if it was with a calculator, we couldn't use it. So we're good without a calculator for these. For this problem, they say that the graph of the continuous function g, which is the derivative of the function f, is shown. So g, they're telling us that g is the derivative of f. I'm going to write that down. G is the derivative of f. G is the derivative of f. So g is equal to f prime. So over here where they give us the graph of g, they're also giving us the graph of f prime. Okay? All right, the function g is piecewise linear from -5 to 3. So from x equals -5 to x equals 3, we have linear line, we have little line segments, linear pieces. And g is equal to this quadratic from x equals 3 to x equals 6. So this parabola is this equation. Part A, if f of 1 is 3, what is the value of f of -5? Well, that sounds an awful lot like a fundamental theorem problem. We have information about f prime. We have information about f prime, and we're given one value, and we're asked to find another value. Fundamental theorem. Let's set up the fundamental theorem where we're going to find f of -5. Since x equals 1 is bigger than since 1 is larger than 5, I'm going to set it up like this. F of 1 minus f of -5 is equal to the integral from -5 to 1 of f prime. Fundamental theorem. F, this has to be f prime over here. for the fundamental theorem. Okay, we're given that f of 1 is 3. We don't know what f of negative 5 is. And this will be the area under the graph of f prime from x equals negative 5 to 1. Here is the graph of f prime. So from negative 5 to 1, we need that area under the curve, right? Well, this area, this part of the curve is below the x-axis, so that integral is going to be negative there, right? So I'm going to count these from negative 5 to negative 2. I'm going to just count those squares. That's going to be a negative 9. And for this little section, it's going to be a negative 1/2. It's a little triangle, so 1/2 base times height. 1/2 of 1 times 3. That takes care of that. From x equals negative 1 to x equals 0, we're right on the x-axis, so there's no area. That's a 0 area there. And on this side, we're up above the x-axis. It's a little triangle, so 1/2 1 times 2. And so positive 1/2 1 times 2. Okay? And now we have to solve this for f of negative 5. So in my mind, I'm taking f of negative 5 to the right. I'm bringing all this mess to the left. So f of negative 5 will be 3 plus that 9 plus that 3/2, but minus that 1 there. And I'm just going to say stop right there. Okay? All right, part B. Evaluate the integral from 1 to 6 of g of x. Well, this is the graph of g, and I just want the area from 1 to 6 right there. So I'm looking from 1 to 6. I need the area under that curve. Okay? From 1 to 3, I can just count squares. From 3 to 6, I'm going to need to set up a little integral for that. So let's go ahead and write out what we're doing. The integral of g of x from 1 to 6. I am going to split this up into the integral from 1 to 3 plus the integral from 3 to 6. So from 1 to 3, that's just 4 blocks, so 4. From 3 to 6, we have an equation for g of x from 3 to 6, right? So we're going to put in 2 times x minus 4 squared dx. And we're going to go ahead and evaluate this integral. We have a choice here. I could square this binomial and find the antiderivative using the power rule that way. I think I'm just going to use a little u sub though instead. So I'm going to go off to the side and do a little u sub on that. U will be x minus 4, du will be dx. So I will have 4 plus the integral of 2u squared du, right? And I left the boundaries empty for a second because I cannot put 3 and 6 here, because 3 and 6 are x values, and I need to make these u values if I'm writing this integral in u's. So over here, when I need to find u when x is 6, and I need to find u when x is 3 to get those boundaries. So when x is 6, u is 2. That's my new upper boundary. And when x is 3, u is negative 1. That's my new lower boundary. So I have 4 plus the antiderivative of 2u squared is 2/3 u cubed, and I'm going to evaluate from negative 2 to 1. And so I get 2/3 of 2 cubed minus 2/3 of negative 1 cubed. And I'm just going to say stop right there. All right, part C. For negative 5 to 6, that's our entire interval that they give us, on what open intervals, if any, is f both increasing and concave up. F increasing and concave up. Well, we know F is increasing when F prime is positive, right? Or 0. F prime is positive or 0. Because for increasing, that's our little, by definition, greater than or equal to 0 there. Concave up, F is concave up when F double prime is positive, right? So I'm going to come down and I'm going to say, so I need for F prime to be positive, and I need for F double prime to be positive. In the problem, I'm checking to see, have we stated what F prime is? We did. We stated what F prime, well, we stated what F prime was right here. So F prime is the graph of G, right? So F prime, we already stated what that is. We did not state what F double prime is, though. So let's go ahead. I'm just going to say F prime is G. F double prime is the slope of G then. So we want where G is positive, and we want where the slope of G is positive. So up here on our graph, we want G to be positive and the slope of G to be positive. Well, I can rule out all of this because G is negative there. This is where G is positive. That's where G is positive. Now I want the slope of G to be positive. So the slope of G is positive here from x equals 0 to x equals 1, and here from x equals 4 to x equals 6. So that's exactly what I'm going to say down here. I'm going to say F is increasing and concave up on, okay, 0 to 1 and 4 to 6. Since, and then we need to say what we looked at there. Since F prime is positive and F double prime is positive. That's what we looked at. So that's our reason. Okay? All right. Part D. Find the x-coordinate of each point of inflection of the graph of F. Point of inflection, graph of F. Well, that's when F double prime changes signs, right? Common mistake is for people to say that it's a point of inflection when the second derivative is 0, but that's not a point of inflection. Point of inflection is when that second derivative changes signs. So make sure you say that. Okay? So I want to know where the slope of F prime, which is the slope of G, I want to know where the slope changes signs. So I'm coming up to my graph. The slope, this is an interesting value of x. X equals -2 is an interesting value of x. This point is because the slope goes from 0 to positive. That is not a sign change. 0 to positive is not a sign change. It has to be positive to negative or negative to positive. So no sign change here. No sign change here. No sign change here. No sign change here. None here as well. The only sign change in the slope occurs at x equals 4. So I will say that. F has a point of inflection at x equals 4, since F double prime changes signs there. And that's all I need to say about that one. Okay. Let's look at how they scored this, how AP scored this. The readers scored this. In part A, they gave 1 point for the integral and 1 point for the answer. So a total of 2 points. So 1 point for this integral right here and 1 point for your answer. In part B, they gave 1 point for the split at x equals 3. So we split it up here. I believe they would have also given you credit for this if you had started with the second line. 1 point for the antiderivative of that quadratic. So 1 point for this antiderivative right here. And then 1 point for your answer. So a total of 3 points. 3 points. For part C, this was worth 2 points. 1 point for the intervals and 1 point for your reason. And in part D, 1 point for your answer, 1 point for your reason. 2 points. So that's how that one was scored. Now let's take a look at number 3 on your worksheet. Number 3 on your worksheet. That was the one from 2016. I can see the way this printed out, it got a little messed up. This is 2016, and you can see the graph kind of, anyway, when I printed it out. No calculator. The figure, oh gosh, this looks awfully, I think on your sheet it actually looks good. It was printed weird here. But anyway, on your sheet it should look good. The figure shows the graph of the piecewise linear function f. So this is the graph of f. And these are little line segments. For -4 to 12, the function g is defined by this. So g is equal to the integral from 2 to x of f of t dt. All right, I know that I'm going to need to say that g prime, what g prime is and what g double prime is. I know I will. So I would like to just go ahead and do it, and then it's done for the whole problem. Okay? For g prime, I'm taking the derivative of both sides to get g prime. So I'm taking the derivative of this integral. That's that second form of the fundamental theorem of calculus. So the derivative of this integral, there's just an x up there, so it'll just be f of x times the derivative of x is 1, minus f of 2 times the derivative of 2 is 0. So the 2 does not matter at all in this f prime. And then for the second derivative of x, will be the derivative of the first derivative, so it's f prime of x, which is the slope of f. So up here where they give us the graph of f, this is also the graph of g prime. It's also the graph of g prime because g prime is f. And then if we want information about g double prime, we will be looking at the slope of that graph. All right, part A. Does g have a relative min, relative max, or neither at x equals 10? Does g have a relative min, max, or neither at x equals 10? Well, we know that g has a relative min if we're thinking of the first derivative test. Since we have direct information about g prime, I'm just going to be using the first derivative test here. You could also use the second derivative test here, right? G the first derivative test for a relative min says that g prime would go from negative to positive. Relative max, g goes from positive to negative. Neither is when these don't happen. Okay? That's the first derivative test. The second derivative test, if you wanted to use that, and we certainly could here, the second derivative test says that g prime is 0 and g double prime, for a relative min, g double prime would be positive. Okay? Positive. Because we would be concave up and have a flat slope. So that would be a relative min. For a relative max, g prime is 0 or undefined here. And g double prime is negative for a relative max, because it would look like that. Okay? So you can use first derivative or second derivative. I'm going to just use the first derivative here, test here. So g has a relative min. Okay, so at x equals 10, I'm asking myself, at x equals negative 10, does g prime go from positive to negative or negative to positive? And the answer is no, it doesn't do either of those, because g prime is negative here and g prime is negative here. This is the graph of g prime, so we're just looking below, it's below the x-axis, so g prime is negative, both those spots. So at x equals 10, g has neither a relative min nor a relative maximum. Since g prime does not change signs at x equals 10. Okay? Part B. Does the graph of g have a point of inflection at x equals 4? A point of inflection, g point of inflection, x equals 4. Well, that would mean that g double prime changes signs at x equals 4, right? So g double prime changes signs at x equals 4. G double prime, remember, is the slope of this graph. Does the slope change signs at x equals 4? Yes, it does. The slope goes from positive to negative. So yes, g does have a point of inflection at x equals 4. So g has a point of inflection at x equals 4 since g double prime changes signs at x equals 4. And that's it. We don't have to say what g double prime is because we said it way up here. We don't have to repeat it. Part C. Find the absolute minimum value and the absolute maximum value of g on that closed interval -4 to 12, and justify our answers. Absolute min, absolute max. On a closed interval, I'm going to set up the closed interval test, also called the candidates test. So I'm setting up the closed interval test, and we know on a closed interval test we have our independent variable and we have whatever we're finding the min or max of. We're finding the min and max of g, so this needs to be g up here. You can put g of x if you like, or you can just name it g, either one. Under our x values, we need to start with our boundaries, -4 and 12. And then we need to put our critical numbers. Well, a critical number of g is any value of x that makes g prime 0 or undefined. Right? Since we're finding the absolute min and the absolute max, I'm going to put anything that makes, I'm going to put those critical values. So G prime is 0 or undefined. Since we have, since G prime is always defined on these boundaries, it's never going to be undefined. So G prime is 0 at what values of x? Well, G prime is 0 at x equals -2, 2, 6, and 10. So those are the x values that need to go on my closed interval test. Common mistake are for kids to put these values of x as well. Well, that's not where G prime is 0, so you don't need to put those. You only need to put the values of x that make G prime 0. So G prime is 0 at x equals -2, 2, 6, and 10. So I need to add those here. And if you wanted to, you could put these in numerical order here, starting with our lowest and ending with our highest, but this will work. Okay. Now we need to find all of these G values. So we're looking for these G values, so I'm going to come back to my problem, the way it's stated. G is defined right here. G is the integral from 2 to x of f of t dt. So that's how I'm going to use this to get my values of x. So let's start by writing that down. G of x is equal to the integral from 2 to x of f of t dt. Well, there's a single value of x that's going to make this integral 0 easily, just from looking at it, and that is when x is 2, right? So G of 2 will be the integral from 2 to 2, and that's 0. So where x is 2, our function G is 0. And now I can use that as my initial value, and I can then set up several fundamental theorems, set up the fundamental theorem of calculus several times to find these remaining values. And that is exactly what I'm going to do. So I'm going to begin by finding G at -4. And since 2 is bigger than -4, I'm going to set it up this way. G of 2 minus G of -4 is equal to the integral from -4 to 2 of f of t dt. G of 2 is 0. So G of -4 is negative that integral. So I need to come find that integral. -4 to 2. -4 to 2. So from -4 to 2, this piece is below the x-axis, and that area is 1/2. Base is 2, height is 4. So 1/2, 2 times 4. Negative since it's below the x-axis. So that's going to be a positive 4. So, did I say that right? I think I did. Positive 4. No. Hang on. Let's see. Oh, I'm not done yet. Goodness gracious. Plus, we're going from -2 to 2. Plus, this area would be, it's another triangle. 1/2, the base is 4, the height is 4. So let me get rid of this here. Plus 1/2, 4 times 4. So I get for not using a pencil. Okay, so this is going to be 8, positive 8. This is going to be -4. And negative of 4 is -4. So at -4, G is -4. Okay. Let's go on. Let's go to 12. So I'm going to set up the fundamental theorem with x is equal to 12. Since 12 is bigger than 2, I'm going to put G of 12 first. Like that. So g of 2 again is 0, so we just have g of 12 is going to equal, all right, the integral from 2 to 12, 2 to 12. So up here from 2 to 12, I immediately see that these two areas are the same, and one is positive and one will be negative, so they kind of cancel each other out. I'm left with this remaining little negative area, right? So negative 1/2, base is 2, height is 4. So negative 1/2 2 times 4, which is negative 4. So at 12, we're at negative 4 as well. Negative 2. G of negative 2 minus G of 2 minus G of negative 2 will be the integral from negative 2 to 2 of f of t. So we're looking for G of negative 2. G of 2 is 0. So G of negative 2 will be negative, okay, the integral from negative 2 to 2. Well, the integral from negative 2 to 2 is just this little triangle. 1/2 base times height, so 1/2 4 times 4. And that turns out to be negative 8. So when x is negative 2, g of x is negative 8. Time to come find 6. G of 6 minus g of 2. Integral 2 to 6 f of t dt. So g of 6 will be, okay, so we're going integral 2 to 6, 2 to 6. 2 to 6 is right here. That is just the 1/2 4 times 4. 1/2 4 times 4, which is 8. So when x is 6, g is 8. And lastly, 10. Keeping on going here. So g of 10 will equal the integral from 2 to 10. 2 to 10. Well, from 2 to 10, that was where those two pieces canceled out, so that's just 0. So g of 10 is 0. So those are all of our candidates, and so one of those has got to be the absolute min and the absolute max. Therefore, the negative 8 here has got to be the absolute min, and the positive 8 has got to be the absolute max value. So I will write that down for AP. The absolute minimum value of G is negative 8. They did not ask me for the x value, so I don't have to say that it occurs when x is negative 2. It's not wrong to say it occurs at negative 2, but we don't have to. And the absolute maximum value of G is positive 8. And our justification was the process that it took to get here. So we are good. I had to cram in a lot in there. Just know that you're going to have plenty of space on the actual AP exam. They always allow plenty of space. So don't worry about having to cram it in like I had to. Okay. All right, part D. For negative 4 to 12, our entire interval, find all the intervals for which G is negative, or 0. So G is less than or equal to 0. All right, so we're back to looking at G. I'm kind of glad we found all of these values of G because this will give us an idea, okay? When x is negative 4, G is negative 4, okay? So if I were just to get an idea of what's going on, I might come off to the side here. Just to get an idea of what's going on, I'm going to plot these values. When G is negative 4, when x is negative 4, G is negative 4. When x is negative 2, G is negative 8. Cram that in there. when x is 2 is next on my list. When x is 2, g is 0. When x is 6, we're all the way up at 8. And when x is 10, we're back to 0. And when x is 12, we're at -4. So this gives me an idea of what's going on, and let's confirm it here. Remember that G prime from -4 to -2, G prime is negative. So that confirms this piece of it. We are decreasing from x is equal to -4 to x is equal to -2. From -2 all the way, we have a little point of inflection here, we have all the way to 6, to x is equal to 6, g is increasing all that way. So we are increasing all that way. And then we decrease. The entire rest of the way. So we're decreasing the entire rest of the way. Okay? So our little values that we found here are very helpful in conjunction with that graph of G prime into saying, now we can say this is the graph of G, right? So we can say all the values of x where G is negative. So G is less than or equal to 0 on -4 to 2 and 10 to 12. That was it. They didn't ask for a justification, so we are good. All right, let's take a look at the scoring for these. For part A, actually before part A, even before part A, they gave 1 point for stating that g of x is equal to f of x in any of the parts, in A, B, C, or D. So in any of the parts, if we stated that g prime was f, then we got that point. However, if you're using that fact, you have to state it. So we had to use it way up here in part A, which tells me we're not going to get the credit for part A if we had not already stated this. Okay? So part A, they gave 1 point for the answer with the justification. So if we had not stated already that g prime was f, we could not have justified it, so we would not have gotten that point. Part B, they gave 1 point for the answer with the justification. That was it. For part C, this involved part, this was worth 4 points. And I'm going to try to cram this in. 1 point for considers x equals -2 and x equals 6 as candidates. So if you put -2 and 6 on your chart, you got that 1 point. 1 point if you considers x equals -4 and x equals 12. Those are your boundaries, so we definitely need to consider those as candidates for an absolute min or max. And then 2 points for your answers with justification. So 4 points total for that. And in part D, this was worth 2 points for the intervals. And that's how that was scored. Now let's take a look at number 5 from your worksheet packet. This was number 20. This was from 2013. It's a little bit of a different one because we have a curvy curve rather than some line segments up there in our graph. Again, no calculator. These will be no calculator questions. All right, let's take a look at this one. I see here that they told me that this is the graph of f prime. I'm sure they'll repeat that down here. The figure shows the graph of f prime, the derivative of a twice differentiable function f on the closed interval 0 to 8. So twice differentiable f, that means f is very smooth, no cusps, no discontinuities, so no asymptotes, nothing funky going on with f. It's a very smooth, nice curve. The graph of f prime has horizontal tangent lines at x equals 1, 3, and 5. So right here there's a horizontal tangent line at x equals 1, 3, and 5. Just like what it looks like it would. Okay? The areas of the regions between the graph of f prime and the x-axis are labeled in the figure. That was very nice of them. So we're not going to have to go find areas this time. They just gave it to us. I like it. The function f is defined for all real numbers and satisfies f of 8 is 4. That tells me I'm going to be using the fundamental theorem of calculus because we have info of f prime and we have an initial point, so we can find any other point we want. Okay. Part A. Find all the values of x in the open interval 0 to 8 for which the function f has a local min. F has a local min. Well, you can either use the first derivative test or the second derivative test. Since I have this nice graph of f prime, I'm just going to use the first derivative test. And I know that f has a local min when f prime goes negative to positive, right? So I'm going to say that. So f prime goes negative to positive. So here's my graph of f prime. I'm looking for where f prime goes negative to positive, right? So here's f prime, positive, f prime is positive, 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 positive. Here it's 0, but then it's positive. So that is not anything. That's neither a local min nor max there. Positive, positive, positive. Here at x equals 4, f prime goes positive to negative, not negative to positive. And here at x equals 6, f prime did indeed go negative to positive. So that is going to be my local min x value. So I'm going to write that down. F has a local minimum at x equals 6 since f prime goes from negative to positive there. That's it. Part B. Determine the absolute minimum value of f on that closed interval. Another closed interval test. X and f, since we're finding the absolute min of f, right? Okay. I begin with my boundaries, 0 and 8, and now I need any value that makes f prime 0, right? Specifically, the absolute minimum value of f is going to be either at a boundary or a minimum or a relative minimum value of f, right? In part A, we found the relative minimum value of f was at x equals 6. So the absolute min is not going to be at a relative max, right? Remember, when f prime is positive, that means f is increasing. So all along here, f is increasing, 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 increasing. And here, it's decreasing. And then it increases again. So this function, f, is going to increase all the way until it gets to x equals 4. And then it will be decreasing, right? And then it will start increasing after 6. So the absolute minimum value of f is definitely not going to be at 4. It's not going to be at any of these values. The only place it could possibly be is at 6 or a boundary, right? So f prime is 0 and goes from negative to positive at x equals 6, right? Only. Now, could we put these other values? Yeah, we could put those other values. We just don't have to, okay? It certainly won't hurt to put it wouldn't hurt to put 1 and 4 here as well. I just know those are not going to be my answers, okay? So, they gave me f of 8 is 4, so I'm going to put that on. F of 8 is 4. And now I'm going to use that with my graph of f prime to find my other values of f. F of 0. I'm going to set this up, so let me change that to an f of 8 minus f of 0, right, is equal to integral 0 to 8 of f prime. Okay, f of 8 they gave me as 4, so this tells me that f of 0 must be 4 minus that integral. And from 0 to 8, the integral will be positive 2. Let's see if I can. So positive 2 plus 6 minus 3 plus 7. Okay, let's figure out what that is here. We have 8 minus 3 is 5, plus 7 is 12, so 4 minus 12 will be a negative 8. So at 0, f is negative 8. What about at 6? F of 8 minus f of 6 will be 6 to 8, goodness, 6 to 8 of f prime. So f of 6 will be 4 minus the integral from 6 to 8. The integral from 6 to 8 is 7, which is negative 3. So I'm looking for the absolute minimum value of f. And here it is. The absolute min, it must be negative 8. So the absolute, let me use correct grammar, the absolute minimum value of f on 0 to 8 is negative 8. Did they ask me for the x value? No. So I can just stop there. Okay. Part C. On what open intervals contained in 0 to 8 is the graph of f both concave down and increasing? Well, concave down is when f double prime is negative. Increasing is when f prime is greater than or equal to 0. So let's find that out. So I have yet, in my problem, I have not stated what f double prime is, so I need to state that. We're given what f prime is, but we have not been given what f double prime is, so I do need to say that. So before I go anywhere, I'm going to say what f double prime is. F double prime is the slope of f prime. Okay, now I can go and use that. So I'm going to go to my graph, and I'm going to look at where the f prime is positive, but f double prime is negative. So f prime is positive, that will be the graph. I want the graph above the x-axis. And I want the slope of the graph to be negative. So above the x-axis and the slope negative. This first little section is above the x-axis and the slope is negative. So 0 to 1 is one such section. So down here, I'm going to, just to make a note to myself, I'm going to say, okay, 0 to 1. Oops, 0 to 1 is one such section. Here it will not work, right? This next section, again, I want the graph to be above the x-axis and the slope to be negative, so 3 to 4 will also work. 3 to 4 will also work. Here, the graph is below the x-axis, so I cannot consider that. And here, the graph is above the x-axis, but the slope is positive. So cannot use that. So these are the only two intervals where the graph is above the x-axis and the slope of the graph is negative. So F is both concave, I'm just repeating what they wrote, concave down and increasing on 0 to 1 and 3 to 4, since F double prime is negative and F prime is positive. You can put equal if you want to, but you don't have to. There. Excuse me. Alright, on to part D. G is defined by this function. Now they like to throw another function in, so now they're telling us there's this other function called G, and it's defined here, and f of 3, they tell us, is now negative 5/2. Find the slope of the line tangent, that's a derivative, to G, so that's G prime, at x equals 3. So we're trying to find G prime of 3. That's what we're looking for. Okay, well, to find G prime of 3, first we need to find G prime of x, right? So here is G. They told us what G is. I just need to take the derivative of this. They're asking me, hey, do you know how to use the chain rule? And I say, yes, I do. So chain rule this. 3, decrease your power by 1, and now take the derivative of the inside. Yes, I do know the chain rule. It's right here. Okay. Now it's time to plug in 3. So we have f of 3 squared times f prime of 3. And I think I can squeeze it in down here. So f of 3, they told me, was negative 5/2. And f prime of 3, well, we have the graph of f prime, so I just go and look at where x is 3. X is 3 here, f prime of 3 is 4. So there is f prime of 3. So just for, and I will say stop right there. Let's take a look at how this was scored. In part A was worth 1 point for the answer with the justification. That was it. Part B was worth 1 point if you considered x equals 0 and x equals 6. Okay? 1 point for your answer, and 1 point for the justification. So 3 points altogether. Part C was worth 2 points, 1 point for the answer, and 1 point for the, they called it the explanation. And part D was actually worth 3 points. 2 points for using that chain rule, finding G prime, and 1 point for your answer. Okay, there are several problems left in this packet for you to try. I encourage you to do these. It's always a good topic on, it's always a topic on the AP exam. So try it. Come ask me any questions that you have.